Hello all, my name is Aitor and I'm the CTO of Telcaria. And in this presentation, I'm going to deep dive into innovative network services exploiting the compute continuum. In this presentation, I will perform a brief introduction of the project, then I will move to the key enablers, and finally, I will conclude with the results that we have obtained so far. Starting with the main objective of this project, the main objective is to achieve network service determinism, which is to improve the reliability and the predictability of network services, to be able to accommodate time-critical and high reliability applications into deterministic network services. In essence, to move from an unbounded traditional network services towards a bounded and deterministic network service performance. The main use cases that are driving deterministic networks today are professional audio and video, electrical utilities, building automation systems, and wireless for industrial applications. However, in this project, we are only going to focus in one use case, which is transversal to the four of these, which is the use of unused reservations by best effort traffic flows, which is the ability to be able to combine deterministic with non-deterministic traffic flows under the same underlying network infrastructure. For more information on the use cases, you can find it in the IETF DEDNet use case RFC. The main limitation that we have identified on deterministic network solutions currently is that most of the solutions are closed source. This is that they limit the knowledge transfer between the different providers. Also, there are very, very few providers of deterministic network services which provide vendor lock-in. Also, these providers require you to deploy their software and the hardware in order to achieve determinism, which is another feature that enables vendor lock-in. And also, normally, deterministic network protocols are implemented in layer 2, which provides for device compatibility. And finally, another limitation that we have identified is that most deterministic networks are deployed as standalone networks, and these networks are unable to maximize the use of network resources. So our value proposition is to tackle the limitations imposed by current deterministic network solutions to offer users tailor-made deterministic and non-deterministic network services that can coexist under the same network infrastructure. Our key enablers towards achieving our value proposition are user-driven requirements, control plane network resource scheduling and reservation mechanisms, data and AI-driven resource allocation, and finally, novel control and data plane technologies. Starting by user-driven requirements, this key enabler enables the user to deploy tailor-made connectivity services where he can define connectivity endpoints, the type of service is going to be deterministic or not, or even specific network requirements, such as the throughput. Additionally, the user can also define dynamic network requirements, such as the one present in SLAs, where the user can negotiate the path reliability KPI, explore the available network resources, or even monitor in real time their network services. Diving into the control plane resource scheduling and reservation mechanisms, we have developed a path computation engine, which is reliability aware by performing flow replication, and also it's best effort traffic aware by performing flow preemption. Diving into the flow replication is the ability to replicate packets at any node in the network topology to increase the flow reliability. In order to identify the need for replication, what we perform is a multipath reliability score calculation, which identifies disjoint paths in the network topology connecting the different endpoints, and then calculates its per path reliability. Moving into the flow preemption essentially allows non-deterministic traffic or best effort traffic to coexist with deterministic traffic. So this traffic will be scheduled whenever there is no interference with any kind of deterministic traffic in the underlying network. As you can see in the figure, we can see that deterministic traffic leaves gaps. So what we do essentially is identify those gaps and fill those gaps with non-deterministic traffic or best effort traffic to improve the network resource utilization and ultimately maximize the utilization of the link capacity. Now moving to the data and AI-driven resource allocation This key enabler tries to identify the gaps that we have seen before to identify where we can schedule best effort traffic. For this, we have performed 3 AI optimizations, namely data augmentation, efficient feature selection, and training workload offloading. So we depart from a generic AI model, we insert this model into this AI pipeline, we perform these 3 optimizations, and then we obtain a model that is more performance to specific use cases. Also, this pipeline is capable of executing in a multiple domain environment where we can deploy this pipeline either in the cloud, in the edge, in the extreme edge, or in any of these resources. So if you want to deploy in the cloud normally, is because you want to leverage low cost of computing resources, while if you want to deploy in the edge or in the extreme edge, is because you have high privacy requirements or limitations, where data is locally stored in your domain. Oops. And finally, the last key enabler is novel data plane technologies. Here in this key enabler, what we want to do is to enhance the network programmability and improve the network visibility of deterministic network services. For that, we're leveraging the technology of P4 pipeline, P4 runtime, and ONF stratum, which enables GNMI and GNOI and network management and operation interfaces which are compatible with OpenConfig. And finally, diving into the results section. In this section, I will explain the main achievement that this project has achieved during the duration of up until now of the project. For HDT SLA, which is a work package of this project, we have achieved deterministic and best effort traffic flow coexistence by developing an intelligent resource allocation mechanism to schedule best effort with deterministic traffic flows. As you can see in the figure below, this is an example of one execution of our intelligent resource allocation mechanism, which is capable of scheduling best effort traffic. And when the prediction algorithm identifies deterministic traffic, it stops to allocate best effort traffic flows and only allocates deterministic traffic flows. And when these deterministic traffic flows stop sending traffic, we identify this by the predictive model, we start again scheduling best effort traffic with the idea of maximizing network resource link capacity. And the result that we have obtained in HDT AI is that we have successfully implemented the 3 AI optimizations that I mentioned before, which are data augmentation, efficient feature selection, and training workload offloading. With an initial model without any kind of optimizations, we inserted this model into the AI pipeline, and we obtained a retrained model with an increased sensitivity for deterministic traffic flows, as you can see in the figure below, where we departed with an initial model. We didn't adapt to our user requirements. This profile is a profile from a specific videos that we have sampled from codec H264. And when we inserted this model into our AI pipeline, we obtained a retrained model that is highly sensitive to deterministic traffic flows, which allow us to schedule better the networking resources in the underlying network. And this is all from my side. Thank you.
Yeah, I think it's very original, the replication feature, because it's something that is usually in a layer 1 in optical network, where you send the same signal to different directions, but not at the packet level. You're dealing all the time with the packet level.
Exactly.
And how do you implement?
We do it with P4, with a mechanism which is cloning the packets in the data plane. So we create a P4, we program a P4 program that is capable of cloning sessions. So depending on the type of reliability that the traffic is required, we clone it or not. And we can clone it at any kind of endpoint. The idea is to identify these joint paths. And once we have these joint paths, we know the reliability the user wants. Then we install this cloning session for a specific flow. It can be per flow or per a group of flows or for all traffic.
Then you discard, how do you discard the replication?
Currently, the project hasn't ended. So currently what we have is the replication and the ingress, or in the middle nodes. At the egress is a little bit more complicated because the data plane needs to store state. So that is a little bit more complicated. But we have done some tests, and usually most applications discard already duplicated packets. So we see it like a next step to implement, but not so critical as to directly duplicate packets at the ingress, which in reality we are obtaining this reliability. Then at the ingress, what we could do is perform some kind of egress function which drops the duplicated packets, for example, using eBPF or something at the Linux kernel, which is quick enough. Because in the network side is complicated because the programmable data plane is not so flexible.